Hey guys, happy Wednesday. Well, it's kind of a cloudy and gray one. Hopefully it doesn't rain all day, but you never know. But today I just want to talk to you guys about negative exponents and what happens when we multiply negative exponents or numbers that have negative exponents with common bases together. So the key thing we need to do is just remember that when we're dealing with negative exponents or exponents in general, every time I drop an exponent, it's like dividing by my base number. So 27 divided by 3 is 9. And then 9 divided by 3, my base number is 3. 3 divided by 3, my base number is 1. So then 1 divided by 3 equals 1 over 3, which if I follow my pattern or my exponent, that would be 3 to the negative first. So then 3 to the negative second would look like this. 1 divided by 3 times 3, which equals 1/9. Okay, if I did 3 to the negative third, it equals 1 over 3 times 3 times 3, which is 1/27. And that's true with whatever exponent. It is just, and some students, what they like to see is they like to notice the pattern. So if we erased all this real quick, okay, and they see that, like, let's say we had 5 to the negative 6th power, okay, instead of drawing out the chart and everything, what they like to do is just say, okay, well, I know if I have a negative exponent, it tells whatever's in my numerator is going to flip to the denominator. So I'm left with 1 over 5, and then my exponent becomes positive. Okay, if I was going to do it looking like at letters, like a to the negative third power, okay, I would say, well, I know that's a negative exponent, so this is going to be in the denominator, so it's going to become 1 over a times a times a, which is 1 over a to the third. Or this just flips to the bottom, my exponent becomes positive. Okay, let's look at f to the negative 7th. Okay, that would look like 1 over f times f times f times f times f times f times f, or, which is equal to 1 over, just take this, put it in my denominator, make my exponent positive. Okay? So that's how we're dealing with those when we're talking about how we multiply. So when I'm looking at a problem that looks like this, a to the third time, or multiplied by a to the negative 7th power, if I wanted to draw that out in expanded form, it's going to look like this. A times a times a times, now this is going to be 1 over a times a times a times a times a times a times a. Okay? And when I combine those, it looks like this. Okay? Notice how, because it would look like that, so it basically looks like a fraction, looks like that when I'm done. Now I just simplify. Anytime I have something divided by itself, so anytime I have an a over an a, I can cancel those out, and I'm left with 1 over a times a times a times a, which is 1 over a to the 4th. Okay? I know it kind of seems like a lot and it seems intense, but when you think about it intuitively, it starts to make a little bit more sense, and you get pretty rehearsed with these. Okay? Now, if I didn't want to do this, I don't have to do it, right? Because we learned the algorithm. So I could not have to draw everything out in expanded form and just ignore it completely. I could erase all this, and I could have just written this like this: a to the third plus, right? And then 3 plus negative 7 equals a to the negative 4th, which is equal to 1 over a to the 4th. Okay? Now, do you have to go all the way to here? No. In fact, if you use the algorithm, it's probably best to leave it as a negative exponent. Okay? So let's look at another one. One more, and then I'll let you guys practice on your own today. So we have, let's say, b squared times b to the negative third. Okay? If that's my case, if I was going to do it in expanded form, it looks like this. B times 1 over b times b times b, which when they combine looks like this, which those cancel, and I'm left with 1 over b as an answer. Or if I wanted to write that as a negative exponent, then it would just be b to the negative first. Okay? But if I didn't want to do all the expansion of it, I don't have to, because I know the algorithm. I can erase all this, and I could have just gone b to the 2 plus negative 3, which is equal to b to the negative first, and I'd be done. Okay? It seems a little weird. Let me actually do one of the more complicated ones that we have to deal with, usually on tests and stuff. So let's just pull this off, and let's do... I'm not going to promise this one's going to be on the test tomorrow, but it definitely might be. Okay, so we have a to the third b squared times a to the negative fourth b to the negative fifth. Okay? If I was going to expand everything out, it would look like this. A, b, b times 1 over a, b, 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 b. I'm going to combine them, and it looks like this. All over a, b, b. Like that. We cancel where we can, and we're left with 1 over, we have an a on the bottom and 3 b's, which equals 1 over ab to the third. Okay? Now, I know that that's a lot of work, and it get lots of places to get confused in there, okay? It's not hard work, it's just a lot of work, so you just have to be pretty thorough as you're writing everything out, okay? But let's just say we didn't want to expand it out. If you expand it out, you'll always get it right. But if you don't want to expand it out, you can always use the algorithm still, even though there's multiple variables. And in that case, we would just take our a's first, and we'd go a, 3 plus negative 4 times b, and that's 2 plus negative 5. So when it simplifies, 3 plus negative 4 is a to the negative first, b to the negative 3, which equals 1 over a, b to the third. Okay, the algorithm or expansion, it doesn't matter what method you prefer to use, they both should get you there. The only catch is if you don't expand and you do the algorithm, they usually prefer positive exponents over negative exponents, but I'm not going to fault you one way or the other. So good luck on your work today, guys. Thanks for taking time to watch the video, and do your best work.